Alright. So today we're going to be talking about particle physics, theory, and hopefully some fun stuff, but more realistically, we're doing a realistic approach to particle physics in that it's hard. So like, see lots of freshmen come in. I was one of them that was like, oh, particle physics is awesome, this is going to be great, I'm going to calculate so many things, but you're not really for a long time. You can do like, so during summer I did Griffith's Intro to Particle Physics book, and a calculation takes like a day. So they're hard, they're not quite easy, but they're still fun, and you'll see. Alright, so the first thing you need when you start particle physics is a lot of math tools and deep understanding of quantum mechanics, classical mechanics, electromagnetism, how to work with fields. So that's why you don't study it during your undergraduate education, because you don't have the rigor to approach the subject yet. So I'm going to derive and show you some mathematical arguments and physical things you need to approach particle physics to a rigorous level, and then we'll also go through discussion of what particle physics means, what these calculations do after deriving that. So on the first page, at the very bottom, you'll see what's called the Euler-Lagrange equation for Lagrangian density. So, let me get this marker. This says partial mu what?
It's a partial Lagrangian.
Yeah. Complete the derivative, that's good. And parenthesis, nice little parenthesis. Alright, so what are these partial mu's? I mean, if most of you are like freshmen, sophomore, you probably haven't seen partial mu at all. So it depends on your definition of what the metric is. In all quantum field theory / particle physics, you use what's called the flat space-time Minkowski metric, which is almost just like Euclidean metric, which is diagonal of 1, 1, 1, just x, y, z, everything else is 0, so you have your measure is dx plus dy plus dz, stuff like that.
What? 130 squared?
No, this is your measure, like your length would be the square, but this is your metric, your measure. So you could call this eta mu for the Euclidean metric, and eta mu.
They should be squared.
The individual elements are squared.
No, I'm not writing your length. These are just the elements along here. So say you took, that would be just a trace. dx, dy, dz. And so then ds squared
Question him again.
Alright. So anyway.
Quadratic form, so you really need squared.
Yeah, well, alright, it doesn't really matter, alright? And so, when you go to Minkowski metric, for reasons that you'll see later, is you get eta mu equals diagonal of minus 1, 1, 1, 1. So kind of you have imaginary time. They stick this minus sign in here, and it's nice and stuff. And it's weird to think whether you actually have a minus sign, you have imaginary time. It's still kind of up to debate, and you use each one depending on how you're trying to approach your problem. You'll see tons of that later. But that's your metric, and then partial mu, which is what we've been focusing on, is, we'll define it here as this. And so the main debate is whether you put the minus sign here or here. And that's depending on if you want minus sign in your metric here or all here. So it's not a big deal. Alright, and so this is your partial derivative with respect to time. and that's your space, nabla. So have you all seen nabla before? Okay, nabla, at least in Cartesian coordinates. Like that. Alright. So, now you have this equation, which is a little weird if you haven't studied Lagrangians at all, or Hamiltonians, so let's apply it to a simple field, just some field phi of t, just depends on time, okay? And so this is essentially a classical field. You could update it to a quantum field that only depends on time. That's non-relativistic quantum mechanics. And so if you plug this in, and so we'll also assume this Lagrangian, which, well, it seems a lot like you're assuming Lagrangians and then you derive fields. Really why you assume a Lagrangian is to satisfy symmetries of the group of the gauge field that you're trying to study. And so, use this phi squared done minus 1/2 g phi squared. Alright. And so, these are just functions of time, and if you plug this into this equation here, partial mu now is only a derivative with respect to time, and what you'll end up getting is n phi double dot plus g phi equals 0. So hopefully this looks somewhat familiar to you guys. If I send g to k, you have the quantum, or classical harmonic oscillator, quantum harmonic oscillator, same equation for both. But in general, this is a coupling constant g. Alright, so hopefully that looks familiar to you guys and you're happy. Another useful thing is Noether or Nether's theorem, and this is used to find symmetries, conserved quantities, which are called your charges or your currents. We're not going to go over that here, but that's detailed in the notes, at least to an extent, and that's important going into particle physics. So I'm going to assume most of you haven't seen what a Lagrangian is, right? Alright. Well, simply, you'll see in like introductory courses is its kinetic energy minus potential energy. Really, it's an energy function on your fields, and you usually use it to satisfy these equations when you do calculus of variations on that quantity. And then you can also, from this, derive what we call the Hamiltonian, which for conserved systems is equivalent to the energy of the system. And this, how you get this is you perform what's called a Legendre transformation, which we're not going to go into here. And you would get, for, say, that field 5t, where pi is called the generalized momenta, and this is equal to partial L with respect to phi. Alright, so yeah, if you use a simple classical field, you would end up getting, and it's just a one-dimensional harmonic oscillator, you would get the actual momenta px. But in general, it doesn't have to be that. You could have angular momenta or just some more abstract momenta. That's why it's called the generalized momenta pi and not p. Alright. So now, gonna say something fun. So has everyone taken Electra? Yes, no? Alright, Casey's taking Electra, great. Well, I'm sorry, but you can derive everything in Electra from like one equation, and using these techniques right here, this Euler-Lagrange formulation to derive equations of motion. That's what this does. You take this equation right here, you perform this, and you get equations of motion. Differential equation that all fields phi in this group, this symmetry group, has to satisfy that equation. So as you go to further higher classes, you'll see more abstract things like the Klein-Goring equation will satisfy another equation, but any field that's a part of that group automatically has to satisfy that for the physics to work. Alright, so everything in electromagnetism can be derived from this guy. Alright, so I already showed you what partial mu was. That was the 4 vector of the time derivative and Nabla space derivatives. And then A mu times E, the 4 vector, rho that's 5. So phi is your electric potential, V sometimes, but phi is a better letter. And then A is your magnetic potential. I don't know if you've all seen this, but I would hope so. And so if you perform this technique, say on phi, you'll get an equation partial mu f mu is equal to mu naught J mu. You'll get something like this. And what this finds for you is 2 of Maxwell's equations. One, J, let me define this. If you plug in J naught, and then you do the derivatives, requiring f mu to be antisymmetric, which you'll get from this form, because if you plug in anything on the line mu, they all cancel each other. So you'd have partial mu, A mu, minus partial mu, A mu. These are all equal, so subtracting the same thing from the self. And then you can work out the off-diagonal elements yourself if you feel like it, and you'll see they're antisymmetric.
You said you get this from applying the Euler-Lagrange equation to that situation. What's actually going on when you are putting A mu into the Euler-Lagrange equation?
So you use the fundamental field A for this, and you plug A into here, and if you were to do that as your
Well,
field.
two questions. First of all, if you need a Lagrangian state your equations of motion, right?
Yeah.
How do
So
you
you
know
want
there's
that?
a current?
There's your Lagrangian. Since most of you haven't seen, some of you haven't seen electro yet, I wasn't going to write that, but if you define this Lagrangian, use A mu as your field, you'll get this. That equation up there. Alright. Alright.
Walked
And then you can also plug in a field phi, just like that 5D, and get more equations of motion for those two. But we're not going to go through the mathematical details, since that doesn't seem appropriate for the audience here. Also, there's another technique that,
So how do you know there couldn't be another current? Could you try to add Lagrangian with another current and see if it works?
yeah, so that's the whole premise of gauge fields and gauge transformations and gauge invariance. So that equation derives the physics, at least classically, that you see in electromagnetism that you get from doing another formulation.
For like the freshmen and underclassmen, what does it mean really when you're applying the Euler-Lagrange equation?
You're imposing a set of constraints that imply realistic physics, like, for example, this is how optics was derived by requiring a method that Hamilton used to derive optics by requiring maximal speed of light it to be c. So you require a constraint with a maximum of your function or a minimum of your function, some constraint like that, and you get the actual physics that comes along. You need to do calculus of variation. So does that answer your question?
Sure.
Good. All right. So anyway, you can do all these Lagrangians, and it's nice and happy, whatever. You get your equations of motion, but this isn't the only Lagrangian that works, because like in this case, you could just say plus some constant, A, or what's gamma, some constant. And obviously, since you're taking derivatives here, that's not gonna have any effect on this set of equations of motion. And essentially, that's just translation, redefining your coordinate system, placing it somewhere new, in this case. But in general, this is called a gauge transformation, where you send, say, phi, your field, any field you have, it could have been A in the electromagnetic formulation, and this creates a new field, but you have to do so that you satisfy what's called gauge invariance, that you derive the same physics, otherwise it's not a good transformation. You don't, that's the whole thing of Lorentz invariance, you don't want to be moving in relativistic frames and get new physics all the time, because then that wouldn't make any sense. Alright, so if you care more about the math, you can read that and also talk to me and we'll go through it, that's fine. But I'm not going to delve on that too much longer. Alright. So let's move on to happiness and Feynman diagrams. So have you all taken modern physics? Yeah. They're in quantum mechanics, man. Alright. So you've at least heard of Compton scattering, I'm sure. Electron, photon, interact, bounce off each other, like they're point particles, but not really, because, for example, photon can be treated as a wave, and there's an interaction. So how this is drawn is, you have this nice electron, you have photon, they come interact, something happens here. You have photon go out and electron go in. What happens here doesn't matter too much, and is usually called virtual particle, something that facilitates the interaction. Because we don't measure here, otherwise we would cut it off, and then this is a whole new physical situation. What you measure is, you send these two particles in, and you get these out. Everything that happens in between is the whole business of making series of these interactions and perturbation series of quantum field theory. It's fun stuff, and they just give you more and more possible things that could happen in here. Like, oh, say this was an electron, it could send off another photon, and it gets absorbed and so on. But that's not too important. What matters is what you get in and what you get out. And this would be a first order diagram. Just, yeah, something carries this information along and then they come back and scatter out in the air. Back where they were going. So this is Compton scattering. You have a photon and electron. Now, wouldn't it be great if we could derive this right now and just move along? We know exactly what happens when a photon and electron interacts at the very fundamental level. But it's not quite that easy. And if you do all of you have packets, that'd be great. If you turn to page 4, you'll see that this diagram corresponds to this lovely equation on the right, which would be probability amplitude. And if you see, it's pretty nasty. I guess I'll write it for those watching on YouTube or whatever.
What kind of probability amplitude does this describe? Really?
I'll tell you in 1 second. Alright. Alright, so that's probability amplitude. Basically what this says is, when these two, the photon and electron, come in to interact, that what happens is this. Probability that this whole thing is what happens. So not like, you could also have, like I said before, a photon be sent out there and then come back in and get reabsorbed again. That is a whole different diagram that creates its own probability amplitude, that's what happens. But, so this is essentially probability amplitude, call it psi, that this happens, and then your probability that you actually measure would be the norm squared, so that you get a number in the end. Now, how you actually derive this, you have to do field theory, do these difficult intervals, usually have minimum 3 or 4 integrals. And since you have 4 particles, at the end you probably have 16 integrals here that you'd have to do. You integrate, this is after the integral, because this one you can analytically solve to this order. So you'll usually have some number inside. Some functions, some delta functions, exponentials and stuff, that determine how these particles propagate when they're by themselves, what happens in the interaction, the potential in this region, and then how they propagate on their own afterwards again. And so this looks like it's extremely annoying to solve, and it is very annoying. Alright, so I can explain this whole formula, like what is this epsilon slash? Epsilon is the polarization vector of the photon, helps give you direction and momentum of the photon. It's energy momentum vector, because that's what you integrate over right here. And then so on, these slashes, you end up having to multiply by these direct matrices because you got fermions, and you get a whole field theory for that, but that's also not useful at the moment, because that's just too difficult. But, alright, so let's see something cool. You can get more from this drawing right here. Say, time moves this way. Now let's say we turn this whole diagram. Let's rotate it so that it looks like this.
I think your initial photon should be propagating in the opposite direction. Towards the electron from the photon.
Well, I rotate it like this.
Yeah.
Yeah.
So the arrow pointing out.
Oh, yeah,
That's the miniature
yes.
diagram on the leading.
Yeah, okay. Well, so this would, basically what this describes is what type of particle, whether it's a particle or an antiparticle. Photon is its own antiparticle. You can just still keep the arrow this way. It doesn't matter in the end. And so, what does this mean? I just told you that if you have an arrow pointing backwards in time, that's basically an antiparticle. They see the universe as different, as propagating in the opposite direction that normal particles see it in. That's weird, right? But that's just life. And so what is this diagram? This was E plus gamma goes to E plus A. Electron scatters off photon. Here, what you have in the beginning is an electron plus what I just told you is an anti-electron. So a positron is actually E plus. And this goes to gamma plus gamma in the end. So if you just rotate this diagram, you get electron-positron annihilation and creation of photons. So that's good stuff.
You said you can put the arrow either way for the photons?
Yeah, because a photon, turns out, is its own antiparticle, so it's the same thing.
So you could just as easily write gamma minus gamma.
Is there a
and
quick
it'd
way
be
to
the
show
same.
that?
No.
No?
Is there a quick way to demonstrate that a photon must be its own antiparticle?
Can you repeat?
Is there a quick way to show that a photon must have be its own antiparticle?
I don't know if there's a quick way. There's a way to show it, but I don't think it's quick. Do you know a quick way? I don't.
No.
Okay. Yeah, I'm not sure there's a quick way to show that a photon is its own antiparticle. You'd have to study the field that would create its spin, because I'm pretty sure it's spin 1, and that's not an easy theory. It's like, for instance, in quantum field theory, we're spending the whole semester on spin 0, which is just like pions, and then a little bit spin 1/2 fermion. So we'll get to this stuff at the end of the semester. So, sure, you can do all these things, and there's a basic recipe of how to do what's called quantum electrodynamics, which is what this is. Photons are the bosons, the field propagators, and they interact with electrons, muons, all these fermions that spin 1/2, spin 3/2, so on, that interact with the photon. And so if you go to page 6, you'll see a whole list of rules that you can find in many particle physics books, internet, wherever you want to go to see these. But essentially there is 9 set of rules that you can then derive anything that happens, anything, quote unquote, in QED. The thing is, once you start adding, very quickly you get infinities and non-analytic integrals, things you can't solve anymore. So this one you can solve. You could determine the integral from these rules, these recipes, plug it into Mathematica as something that integrates with, or if you're really good at integrals, possibly do it yourself in a while, and it'll give you a number. It'll give you a probability amplitude. But you can't solve all these, or else we know a lot more than we do know. We would still need experimentation, but we'd have a lot more theory in particle physics, I'd say. All right. So let's move on to what is quantum field theory. So I'm just going to show you 2 things that are pretty cool, because if you study quantum mechanics, you'll see that you get results that are very similar to that. So if you study quantum mechanics, you see that most things like the unitary operator, the time evolution operator, is derived from using the Hamiltonian. Changing the eigenstates, the energy eigenstates, or the wave function that you're studying. How does it propagate in time? Do you get new particle states? So in general, when you have a quantum field, you get particle states that not only can propagate and change their own wave function, but they can change into a different number of particle states. And so in quantum mechanics, you have an integral that's kind of like a dagger A, it's an omega. And if you act with this on states, you'll get you'll generate single particle states with certain energy and momentum, and omega determines this. Now, this all can be derived from the Hamiltonian operator. And so this doesn't make an insane amount of sense to you, but when you look at the Klein-Gorn theory, you'll see that this does make sense, because what that shows is that you have this, or maybe not squared, acting on a field is equal to 0. I should use the same field, E. And so this is very reminiscent of that in that you could treat this as Lagrangian, and then this would be the Hamiltonian that you could get from the Legendre transform on that. And then if you work it out, plug in phi in terms of annihilation and creation operators for the field, in terms of single and multi-particle states, you'll end up getting a Hamiltonian, omega, A dagger A, plus a constant. So you get the same exact integral that you got in non-relativistic quantum mechanics, which is, you study in undergraduate.
What are A and A dagger?
Right. They are the creation annihilation operators. So if you have A dagger acting on 0, this will create some state, okay, some momentum, some particle state.
What is 0? What is that?
0 is the vacuum state.
What's your measure for H over there? Well, if it's the
Oh.
manifestly Lorentz invariant measure, won't the like hidden over 2 omega k cancel?
dk tilde,
Okay, feel that?
which is Lorentz invariant in its own right.
Yeah, but it's Lorentz invariant because it's like dkx, dky, dkz over 2 omega k.
Yeah, and so, and omega k is itself invariant along with these operators, so this whole thing turns out to be Lorentz invariant.
So if you move, so if you cancel it out, it's just like dk, 1/2 dk cubed times
Yeah.
accretion and annihilation.
Yeah, this is just a little more compact than writing it that way. Yeah. So it turns out this Hamiltonian is Lorentz invariant, which is nice for the Klein-Born field theory, but I wasn't going to go into that here, so I won't.
Well, the theory is completely generated on the fact that it should be Lorentz invariant.
Yeah. But a lot of people might not know what Lorentz invariance is in here. That just means if you transform to a different special relativistic frame, you get the same physics. That was derived by Lorentz and Einstein, and that's called Lorentz invariance. That's kind of like the gauge invariance I was saying. That's switching gauges, switching to different special relativistic frames, and you get the same physics. That's gauge invariance. Alright, so you get this Hamiltonian. The same thing you would get in normal quantum mechanics. And then this constant. Guess what the constant is? It's infinity. Plus another constant. It's infinity because of this vacuum. What you're doing in this is, what you actually have is a dagger without this constant. And then using commutation relations, which you'll learn between A and A dagger, which is defined to be A dagger minus A dagger A, and no units because who cares about those? Something like that.
They're all one.
Yeah, exactly. H bar equals C equal 1 here, so don't worry about those. You'll get something like this, and here you switch the dagger using this, and then you get a term in your integral which doesn't depend on k. So you're just integrating over all k's of this number, c. And so if you're integrating over all k, you get infinities everywhere. So basically you're integrating, summing up all the energy momenta of the vacuum and relating it to non-relativistic quantum mechanics. If you solve the quantum harmonic oscillator, you get n plus h bar omega over 2. That might be over 2, but you get
H bar omega n plus 1/2.
so you get some energy levels for quantum mechanics. This is from raising to different energy eigenstates for the particle. But if you're even at the 0 state, just 0, the vacuum, you have this 1/2, n equals 0. But you still have 1/2 h bar omega. And basically what you're doing in that integral is summing over low vacuum states in every single position in space-time. Every single position, there's a vacuum particle state, vacuum ket. You have this 1/2 h bar omega there, but you have infinite of these spots in space-time, so you have infinite energy. But we don't see this because we measure with respect to the vacuum. And so what I would do, or what Tan would do in his class, is just set this constant here equal to minus that constant. And now you can forget those guys. You just have that lovely Hamiltonian, same thing you used to have. But now you can generate multi-particle states with this. It doesn't just have to be single particle states, because you can act with multiple Hamiltonians, H prime, generate all the states you want. Obviously there are restrictions which nature tells you not to do certain things, but don't listen to it. And very nicely you get somewhat of a symmetry. So you have that's an ugly H. Isn't that home? But you can also derive a momentum operator. And this, surely enough, is where K would be the momentum. So omega is essentially the energy of the quantum state, and K is the momentum of the energy, or of the state you're acting on. So you act on some state 0, and you get some momentum eigenstate K when you do that. Or if you act with the entire integral, you get all possible states. So it's interesting that you have this symmetry. Essentially all you switch in these, omega goes K, because you have a momentum forward vector, P, is equal to H, or plus or minus, however you define your metric, and the momentum. So it should be this way. And you also see, and I won't say that because some of you might not know the Heisenberg equation of motion. All right, so let's derive QED. All right. So, like I said over here, the way you do these theories is you start studying some group, like QED, it's U1, a unitary group of 1, which is essentially all elements that can be transformed between in the complex plane. So you have some element x, and then you go to another element y by this transformation, where phi is some angle. In the complex plane. So this is how you get to different elements in this group. You start from x, and it sounds complicated, but all you have to do is a rotation and multiply it by a number. That's why it's called U1. If you attach this s, which unfortunately QED doesn't do that, then everything is the same length. You just have a circle in this plane, but that's not what this is. You don't have a circle. All right, so let's start from the simple Lagrangian. It's not so simple. It's on the bottom of page 7. All right. So I showed you what this guy is, minus 1/4 F mu nu F mu nu. That comes from electrodynamics, classical. That generates fields in there along with the J mu A mu term. But what is this? Psi are fields. They're fields of your particle states. You can have electrons over here in this space-time, you can have photons, They don't really take up a point, but just trying to make a graphical representation. It's just some superposition of particle states, and that's your field. And we call that psi. And then you have derivatives, which is d mu. We define it here in such a way just to make things a little less writing, for lack of a better word. So d mu is defined to be partial mu plus I. So that's just the normal derivative I showed you in the beginning. And then this is the potential with electric charge, which in general is the coupling constant. So the coupling constant here in QED G is equal to E, the electric charge, which is really nice to have.
What is psi hat here, Lagrangian?
Yeah, that's called psi bar.
Psi bar, sorry.
Yeah. I was about to define that, but that is just, it's defined in the notes too. Psi dagger with a gamma mu after it.
So how do you vary sidebar and side dagger properly in the Lagrange?
How do you vary them to maintain gauge endurance?
Well, yeah, how do you take the derivative properly?
Oh, so you can just do the same thing as you did before. So you could plug in here psi. You could also plug in psi bar. You treat psi and psi bar as their own field operators, and then you plug in here. If you do, yeah. So you essentially have three fields that you can act with and find the equations of motion. You can do psi, psi bar, or hidden in here and here are A. And that's a field of your electromagnetic field. It's the potential that generates that field. So you can treat any of those as your fields and then perform Euler-Lagrange methods to get equations of motion. And you'll find three. So the first two will be so if you did Euler-Lagrange on psi, you'll do this here, this method. You have a partial mu psi here, so you'll get a psi bar I gamma mu. And then here you'll get, you'll get an IE A mu. And this will all be multiplied by psi bar. So you'll have an equation for psi dagger because I defined psi bar to be psi dagger gamma mu. So you'll have an equation of motion for the complex part of the field. And then you can just take the conjugate of everything, the complex conjugate, psi dagger, or Hermitian conjugate of everything, and you'll get an equation for psi. They're essentially symmetric. You just take complex conjugate of each equation to get the other.
Did you
Yes.
say what gamma mu was?
Oh, I didn't, sorry. So gamma mu is what's called the Dirac matrix. So it's a 4x4 matrix of, I think this is the identity, 0, 0, maybe minus 0, something like that. And where this is, these are 2x2 matrices, so really this is that. So by each of these things I mean a 2x2 matrix where one is the identity matrix, so it'd be minus identity, identity 0, 0. And then similarly for, well, not quite so. I'm trying to be sigma I, 0. These are all 2x2 matrices again. And sigma are your polyspin matrices. So if you've been in quantum mechanics class, you'll see sigma 1, I guess, is 0. Sigma 2, 0 I minus 0, and sigma 3, 1, 0, 0, So these are polyspin matrices. They basically show you how to do rotations in U2 or SU2, the complex 3 dimensions. And so the gamma is the Dirac matrices. A 4x4 matrix is composed of these matrices. It's ugly. But you work it out and you get this equation of motion, which is nice. And this is how some wave function psi, some superposition of particle states interacts with quantum electrode field, QED. And so, say you plugged in an electron, you could see exactly how it's supposed to move. But you can't quite solve this differential equation analytically all the time. Most times you can. And it gets more complicated because this is one of the simplest fields, the second most simplest field equation. The Klein-Gorham, which I showed you earlier, being the simplest because that describes spin zero. You don't have to take into account an extra dynamical variable of motion. All right. And so now, there's also this A mu, which I said you can treat as its own fundamental field. And you can perform the same procedure again, and you'll get another set of equations. This guy. So we won't go through that here, but I mean, I could work it out after the lecture, and it's essentially just applying this, but phi is now A. And it's not that difficult if you just keep track of your minus signs and such. And so what you get is this. F mu nu is the electromagnetic field tensor. So what does this describe? This describes how the field, the electrodynamic field, propagates in time, how it changes itself in space-time. This pretty much is telling you that this is how photons are generated. Because what a photon is the vector boson that changes the electromagnetic field, or is caused by changes in the electromagnetic field. Interactions with this field that you can think of like space-time, but it's not space-time, it's like it. And it's propagating and it has its own motion, and then interactions within it create resonances that are called these photons. And then another thing that's cool is A mu has to at least be on the order of some quadratic function for there to be a photon generated. Because essentially what you have here is second derivatives of A, because F mu was defined to be this. You have first derivative of your A's, and such that's anti-symmetric. And then you take the derivative of F, and you'll get second derivatives. So basically, if you write in a polynomial expansion, it has to be at least second order for anything that's not just a constant to be generated. And particles are not constants. They move. Because if you simply got a constant, some number c, you can move this field, translate it to a new frame, and you'll have zero. And so there's nothing. So you have to have at least that quadratic field to generate even a photon, which then interacts with the electron in the Compton scattering diagram, further diagrams to create phenomena that we see. All that you have to have at least that. Okay. So, I mentioned that this was a U1 group. U1. So, how do we transform to maintain this gauge invariance? What do we do? How can you change psi, look at it in a different way and get the same physics? I essentially answered that earlier. You just do a rotation, e to the minus I phi, some different number, I don't really leave it phi since the fields are phi, acting on phi, and this is your new state. And if you look at it in this way, and plug it in to these equations, you'll get the same thing. You'll end up being able to just cancel out the exponentials, and you'll have the same physics generated in the end.
So for phi, it has to be a spinner, otherwise,
Yeah, we're not gonna go into what spinners are because it's complicated. Don't
you
really.
just need to know they're like, 4 vectors, complex coefficients.
Yeah, they are essentially just vectors with complex coefficients, so they have 2 dimensions of dynamics each. And then you have a particle state and an antiparticle state. But to actually talk about what those are takes a lot of mathematics, and that take at least an hour to do. So it's not completely useful here. Alright, so that's how you can do a gauge transformation on your field phi, your particle field, to get a new particle field in a different frame that generates the same dynamics, the same physics. How can you change a mu? The only way to do this is to add a mu, some derivative, some simple derivative that when you take the second derivative, you don't get anything in the end. The second derivative is 0. And when you do Lagrange equations, you'll take second derivative of that, you'll get this, and that's 0. That's the most general thing you can do to maintain gauge invariance in the electromagnetic field. So, both these show that there is no special frame. Either in electrodynamics, there's no special potential. You can add this simple first derivative, that's like a constant first derivative, or you can rotate in the complex plane the field itself. Look at it another way and you see the same thing. So there's nothing special about how you look at something, except sometimes it's easier. Not really in this case though. The most useful case in actually driving things is set that to 0 and just use phi. But you can always transform to a new frame under these constraints in U1 to get a different field. Okay, so that's the bulk of the material that I have for you, but I'd like to say a few things about field theory and particle physics in general. So this is all scary and it may seem like you assume much, like these Lagrangians, these symmetry groups, U1, why do you assume these? It's not completely clear why you assume these, but QFT has produced the best calculations that man has ever created so far. For example, the magnetic moment of the electron, which still makes no sense at all, because we still tend to treat it as a point particle, which should not be so if you have a magnetic moment. We have calculated that up to 10 decimal places, and nothing else past that, and found it experimentally to pass that. We have calculated to a third order and found to fourth order the correct result. So everything we've calculated we have correct for the magnetic moment of the electron, which shows that this theory, at least here, is correct to a very good extent, to 1 part in billion, million, something like that. Very good results. And I was going to say a bit about what LHC does, but I feel like Robert next week is talking about nuclear physics and stuff like that, but he's not here. So, at least how I see it is, the LHC measures what's called these resonances. When you do these integrals, you'll often get things integrating over, say, dk tilde, 1 over k squared plus omega naught squared. Something like that. But in special relativity, this k squared can be negative. It doesn't have to be positive. And so this term can be 0. K squared plus omega naught can be 0 at some point, which would generate infinity. So that's essentially a resonance. And if you, when you try and deal with these analytically, you want to avoid those. But we see these, we see resonances, peaks in these distributions, like say the Higgs boson, when you look at the graph, what they look for is a resonance spike and try and see if it's a signature that corresponds to what's been theoretically calculated. So what a particle is, essentially, is a resonance, an energy packet that stays for a little while. The time it stays is dependent on the theory, how fast things interact. Like wave theory is something like 10 to the minus 17 seconds. So a lot of times it can be very short. But that's essentially all a particle is. Alright, and the last thing I'd like to say is this approach to looking at QED is how you approach all quantum fields, essentially. You start with some symmetry group, U1 here. You could look at SU3. That corresponds to 3 particles that can transform between each other, which are the up-down strange quark, is our group for looking at that structure. And then you look at a Lagrangian that would satisfy this symmetry group and gauge invariances within this, how this symmetry group transforms on its own between different fields in there. And then you generate all these equations of motion that we derived here for different field theories. And see how that produces. Sounds simple, but it's incredibly hard once you get past things like this. Alright, and what we have in the end, what LHC looks for, is confirming the standard model. It's this great thing, all these composition of groups that we have, QED, QCD, the weak theory, and I'm not sure if the graviton fits in there, but it'd be nice. And so, we have this model, all these particles that we pretty much theoretically calculate everything in the standard model. And we're trying to fill it out, and we're almost done. But in the past few decades, we've started to see a lot of things that don't make sense from the standard model perspective. For example, SU3 for the quarks doesn't make much sense because the reason you assume that is you set their masses to be pretty much equal. But we've measured their masses, and the strange quark is pretty heavy compared to up and down. They're not even equal either. They have slight differences, but it's small enough that you can approximately assume a group SU2 for just those two, and you get good results. But when you do a third, you don't quite get perfect results. And if you try and add in a fourth, and we know that currently there are 6 quarks theoretically, and we've measured 5 of them, you don't get good results at all. That's why no one talks about SU6, because you won't get results that work well because of the differences in mass become increasingly large.
But the SU3 gauge group for QCD is fine, right? And for an SU2 for the...
Yeah, it's pretty much fine because it would create errors that we can't measure at least any time in the near future.
But you can treat the quarks as like another SU3 group, right?
Yeah, at least up, down, and strange. And then the others, you could try and make it their own group, another SU3 of the heavy quarks, but they're still pretty different in masses in their own right with respect to the other heavy quarks. So it still doesn't work out quite as well as we would like it to in the end. So recently, in the past few decades, we have encountered lots of things that don't make any sense to standard model physics. Like dark matter, we have no idea what that is. There's speculation that there are multiple Higgs bosons, not just one. Standard model is cool with 1 being there, but not really cool with like 3 being there. That would suck, at least for the model we currently have. Or sterile neutrinos. I don't know much about sterile neutrinos, but they don't really fit in the standard model as well. All of these show that what we have is essentially just a subset of what the true theory is. There's all this physics happening, and surely there's much more physics happening at higher energy scales that we can't even measure yet, that we're not seeing. But hopefully, as we form all these group structures and discuss this, these groups are just subgroups of the true group. At least that's what I'd like to believe.
Is
That
there
there's
anything that keeps you from just adding another term into the standard model Lagrangians and all these things?
no, there's nothing that keeps you from doing that, except that it won't generate the right physics in the end. You can add all you want. In the standard model, Lagrangian is like a page long. Like it's easily take up this board. You just find something new, tape it on there, keep going, be a little more happier because we derive some new physics. But in the end, there's something more fundamental that's happening that we can't really account for. But what I like to believe is there is still a group structure that we can analyze in somewhat of the same way, maybe not exactly. Some new mathematics may need to be generated, but this method and these structures are too nice to not be actually happening. All right, that's all I have for you. Any questions? No? Was it too hard?
I know
I warned
fundamentally
you.
this came out of, fundamentally a lot of this came out of like applying relativity to quantum mechanics. And what generated like thermodynamics past that? It's just applications of field structure and everything.
Yeah, it's the subject of gauge theories. I'm looking at